Today I'm going to talk about the paper discussing about the multi-agents, cooperative multi-agent system. So this paper was published in AAAI in 1998. This is the outlier. This is the outline of the presentations. So first we will discuss about the little bit about the multi-agent system. Then we go very quickly through the Q-learning approach, and then some of the method that we try to cooperate the multi-agents in the system, and then we evaluate them through some of the game they usually do in the multi-agent system, and then jumps to the conclusion. So what is the multi-agent system? It's obvious, right? Because it has many agents inside the system. For example, we have two agents inside the system, and every some step, each agent will make a decisions on the actions, and then get the reward. So, uh, so that is the definitions of the multi-agent system. But this paper they focused on the cooperative environment. What does it mean by cooperative environment? Cooperative environments mean that the actions is the joint actions, and the reward is the same for both agents. So this means that every time step an agent choose their actions, and the reward will depends on the actions of the choice action they are making. So, for example, in this case, if the agents one choose A1 and the agent two to B0, then the reward will be zero for both of them. So, which means that now the agents is not fully control the reward they're going to get from the environment. Uh, and one more thing is that this papers is focusing on the single stake game. So which means that there is only one stake in the system. So that is a definitions of the multi-agent system. So I am assuming that everyone is familiar with the Q-learning approach. So it just go very quickly. So the task is to estimate the expected reward of taking any actions from the step. So but for now we are focusing on a single step. So the Q-learning will include three steps. The first step is we need to choose the actions based on the value of taking one actions, and based on the what I call is the exploration strategies. We could be epsilon ready or stuff. The second step is that we taking that actions and observe the reward, and the last step is that we update the value for that actions. So I just mentioned the Bosman exploration strategies because in the paper they use it. So basically, the Bosman strategies say that we are making the choice of actions based on the Q value of every actions by the submap functions. So the one more thing is that the t value here is the parameter that control the randomness of the sampling process. So which means that in the strategies there are two parts. One is the random and one is the rational. I mean that we can choose the actions randomly, or we can choose in a rational way. So rational way is that we choose the actions that give us the maximum reward. So that is the Q-learning. So in the multi-agent learning, so there are two type of agents. So two type of learner. So the first one is the independent learner, and the second one is the joint action learner. So let's see them one by one. So for the independent learner, it's simple. It just treat the environment and the other agents as its environment. So every time it's just making decisions on the actions, and they will give they will get the result. They will get the reward. Completely ignore the other exists of the other agents. So the agents will learn the key value for each individual actions. For example, in this game, the agent one have two actions, so the key value they so it has two key value for A0 and A1. So there are reasons to apply this kind of learner. So first of all, the agents one may not be aware of the existence of the other agents, uh, or it could be that it cannot identify the other actions of other agents, or simply it don't believe that the other agents are following any kind of strategy, which is makes sense, right? Because we are cooperating, but we don't know our partner exists, or we cannot know that what are they doing, or we don't believe that they are doing something helpful. So we just the symbol is solution. The solution is the symbol, right? We just ignore them and learn our key value. So everything remain the same as the Q-learning approach, Q-learning algorithms. So that is for the independent learner. So for the other type of learner, which is the joint action learner. So in this time, the agents is aware of the existing of other. So which means that they have to learn the key value for every joint action. So for example, in this case, agent one have two actions, agent two have also have two. So agent one will have to learn the key value for joint actions. So but in the Q learning approach, so the first step is to make a decision on the actions you want to perform, right? So how can we calculate how they come the helpfulness of the taking one individual actions? So it's simple because it's just the sum of the joy 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 value weighted by the estimations of the other agent strategy. So what is the estimation here? So the estimation here is just the so every time we make a decision on the actions of our choice. So the other agents also do. So we start counting, and then eventually we will form the belief on the strategies that other agents are playing. So for example, here we have agent one and agent two, and every time agent two pick the B0, and then agent one will count it, and eventually it will have the informations about the strategy the agent two are playing. So it just if they want to evaluate the actions, the value of the individual actions A0, you just weighted with that strategy with the joy action. So that is the how the joy action learner work. So let me go back here to the Q, Q learning approach. So the first step is to choose action, right? So to choose action, we need to have two type of informations. One is the exploration strategy, And the second is the expected reward you want to get when you are taking individual actions. So for the independent learner, it just use the Q value for that action, and for the joint action learner, it will uh, take more informations about the order strategy in order to calculate that value, like in this function. Yeah. So that is the main difference between the independent learner and joint action learner. Uh, the second step and the third step they remain the same. So let me go to the climbing game first, because in this game we will see that very interesting phenomenon. So in this game there are two agents. So each of them have three actions to choose. So if the agent one choose A1 and action two to be 0, then both of them will get a reward of 11. But if the agent two to be 0 and agent one to A1, so both of them will get punished by the value of minus 30. So that is teamwork, right? So how do they proceed? So as the beginning of the training process, each agents have nothing about to do, so they randomly explore the three actions they have. So agent one will pick the actions randomly, A0, A1, and A2. But for a while, agent one will start to see that the option A2 is better than option A0 and A1. Uh, the reason why is that whenever action 0 is big, it may be punished by the values of 30 minus 30. So it will find that action 2 is better than the than 0 and 1. So it will start play mainly by action 2. So the same for action 2. So both of them for a while after the randomly picking, they will stick with this type of strategy. So at that time, agent one mainly play A2, and agent two mainly also play B2. So for a while, because the action two, they observe that Agent one always mainly play A2, so they start seeing that the option B2 is better than option B1 is better than option B2. So they start moving from B2 to B1. So then at this time, they both agent two will mainly play A2, and actually agent two mainly play B1. And once again, agent two will eventually see that the action one is better than the action two, so they start moving to the action one. So both of them will be mainly play their A1 and B1. So you see how the corporation have to improve the performance of the reward. Uh, so here is the plot showing the probability of choosing each actions as I just described above. So first of all, three options, the probability of three options is the same. So then the agent one start interesting in the action two, and then it will change its interest into the action one and stick with the local optimal there. The same for agent two. So in this slide, in this slide, they gonna show the how the structure of the game can affect the convert. So basically, it's the same with the previous one, but in this case, the punish is k and k suppose k is minus 100. So the same as before, right? So Asian one will start to see that option A1 is the best, and also for the Asian two. So both of them will mainly play A1 B1. But when the key values is the k value is going to zero, which means that the agent one will less likely to see the difference between the action A1 and the other. So it means that when k go to zero, they will convert faster to the optimal solution. So as you can see from the slide, the slide is the probably the likelihood of the convergence to the optimal joint action. So when k approach zero, the convert will be very very fast. Another thing is that in the parameter setting, if the temperature decay is high, which means that we uh, we want um, we want to get we want to get, if decay temperature is low, which means that we want to the sampling process to get more random actions. So that's why it will convert lower than the other. So that's why we have two curves here. So the same thing happened for the independent learner too. So they also have some conditions on the convergency. So the first two is actually the convergence condition for Q-learning, and they also add another two. So then the reason is simple, right? The third one is that the probability of choosing an actions must be non-zero, which means that you at some point you have to give the other action some kind of the chance to be big. So which means if at that point the agent one always choose action two with 100%, then there's no way to get into this position, and so on. And not the last condition is that the exploration strategy must be exploited, which means that at any point of the time, your agents must have the motivation to achieve more reward than the current one. So that's why they can move from here to here and to here. So for the conclusions, I would say that there are two simple ways to apply the Q-learning to the multi-agent system. One is the independent learner, which is just a solution that you simply ignore your partner. And the second solution is that we observe the actions other are playing, and then we make assumptions about the strategies they are following, and then taking more care about evaluate the actions. And one more thing is that we can come up with the strategies that more biased to get the global optimal. So which means that in this case we can derive with the strategy that biasing toward the reward so that the both of them can get from 7 to 11. So I guess that is all.